Guys, are you excited? We are finally learning calculus. Yay! Like, and you're thinking, what? We haven't been doing calculus this whole time? I've been drowning. Okay, no, remember we've just been like reviewing algebra and stuff. But today we learn calculus. Finally, we learn calculus. And I need to take my math geek down about 5 notches right now because you guys are probably not nearly excited about this as I am. Okay. So today we're learning about limits. They're the first thing of calculus that we really get to learn. So basically in calculus, there are three main ideas. There's limits, there's derivatives, and there's integrals. And what you'll find is they're actually really related. They're so closely related that they're practically the same thing. So we really only learn one thing in calculus, but that's not here or there. But anyway, we're learning about limits today, which is our very first topic in calculus. So what is a limit? A limit basically says we have some point on a function, okay? And we're trying to figure out what is going on with the value of that function as we get really, 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 really close to that point. Now, I want you to remember that when I talk about the value of a function, or when I say, what is the function doing right now? What am I talking about? I'm talking about the y value, right? When I say, is the function increasing? Is the function decreasing? That's talking about the y value of a function, right? So if I'm saying, what is the limit of a function, it's going to be a y value, right? Because this is like, what is the function doing always means what's the y value going on at such and such a point, right? So the idea is if I say I have this limit and I want to know what's going on with the function as I get really, 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 really close to this y value, or actually as x approaches a certain value, what's going on with y? And maybe as x approaches from the other way, what's going on with y? So let's take a look at some examples. Here we have a graph. Imagine that this is like the path of a bouncy ball. Yeah, this is a bouncy ball. Okay. So this is the path of a bouncy ball, and here it goes up and down on the table and down, then down off the table and into the abyss of the asymptote, and then it just reappears. Anyway, so if I would say like as time, so we could say x is time. A lot of times we think about x as time. As x gets really, 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 really close to -4, what's going on with the function? What's actually happening on this function? Well, as we get really, really, really close to -4, the height of this bouncy ball is about 1. Even if I'm not quite at -4, right? If I'm at -4.1, or what if I'm at -3.9? I'm still getting really, really, really close to being at a height of 1, right? That's the whole idea of limits. The whole idea of limits is what's going on when I get really, really, really close to a point. So maybe at this point, we have the same question. So what's happening at time equals -1? And I know what you're thinking, there's no such thing as time equals -1. But imagine that this is time, like, this is 1 o'clock. Or not 1 o'clock, noon. Sorry, this is noon. So this could be like, time -1 would be like 11 a.m., right? And then this would be 1 p.m. Anyway, so as we get really, 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 really close to 11 a.m., what's going on? Well, right at 11 a.m., this bouncy ball just like teleports into a different height, right? It just teleports down here and it's now at 1 instead of at 4. But what's going on as we get really close to -1? Well, we're approaching 4, right? And so the idea behind limits is that we don't have to have a continuous function to be able to figure out what's going on around a point, right? Because if you remember continuity, this actually has some discontinuities in it, right? Because remember, discontinuities tell us where I couldn't draw without lifting my pencil. So I'm drawing here, I can keep drawing on the function, I can keep drawing on the function, I can keep going. But then when I get right to here, I'd have to lift up my pencil to be able to keep drawing, wouldn't I? So there's a discontinuity here. And so oftentimes we can't deal with functions that have discontinuities because they're not continuous. But limits tell us what's going on right around that discontinuity. So even though we can't figure out like exactly what's going on right here at 4, or not at 4, excuse me, sorry, at -1. At time equals -1, we maybe don't know exactly what's going on, but right around that, we can figure out what is happening. So we can get really close to what's going on. Okay, so the best way to learn limits is to practice limits. But one more thing that we really need to talk about is that, remember, limits are a y value. So when I say, what is the limit as x approaches some number, your answer is a y value. Your answer is a y value. Limits are always y values. And then let's talk about how we're going to write limits, okay? We're always going to write limits the same way. You are never, ever going to write the limit equals 3. Don't do it, okay? You're also never going to write as x approaches 3, y approaches 2. You are never going to write that, okay? I'm just telling you right now. Can't write that. What you are going to write is you're going to write the limit as x approaches some number. Let's just call it c. Right? The limit as x approaches some number of our function. So if you know your function, you can name it. You know, if it's already named f of x, you just write f of x. If you know the function, like if it's x squared, you can just write the function in like x squared, equals some other number. Okay, so this c is a number, this L is a number, and then f of x is some function that we often are given. Okay, so the limit as x approaches some number of f of x equals another number. Okay, that is how you're always going to write the limit. You are always, always, always going to have this notation of limit, and you're always going to include the function because that's proper notation. Otherwise, a lot of times what you're saying is that some function equals this number, and it doesn't equal that number, where the limit equals this number, okay? So that's my soapbox for limits. Now, let's take a look at what they actually look like. So the first one, number 1, it says, what is the limit as x approaches -4? So again, what is going on right at time equals -4 for this bouncy ball, right? So at time equals -4, how close, what are we getting to? Well, we could do something like called direct substitution, basically, where we say at -4, what's going on? Well, at -4, y equals 1. Right here at -4, y equals 1. And then we just check, we can check on either side. Does it work as it approaches that from the left, and as it approaches from the right, is it also getting very close to -1 or to +1? Yeah, absolutely. You know, so at like -4.0000000001, it's basically at height of 1, right? So the limit as x approaches -4 of f of x is 1. Okay? Let's look at the limit as x approaches -1. As x approaches -1 from the left, we're getting very, very close to 4. And then as we get from the right, we are also getting very, very, very close to 4. Now, this is super important about limits. For the limit to exist, they have to be approaching the same number from both sides. So in this case, they are approaching the same number, right? As you come from the left, it's approaching 4, and as you come from the right, it is also approaching 4. So we could say the limit as x approaches -1 is 4, because from both sides, it's approaching 4. Now let's go back. Actually, I forgot to talk about the function values because I kind of mentioned it but forgot to write it down. So what is the actual function value at f of -4? When x equals -4, y equals 1. But then what about when when x equals -1? What is the function value? It's actually 1, right? Because that's the actual point on this graph. When x equals -1, y equals 1. It doesn't equal 4. It equals 1. But where is the graph approaching as x gets really close to -1? Well, it's approaching 4. So do you see how the limit and the function value are actually kind of two separate things? If the graph is continuous, the function value and the limit are going to be equal. See, when we've got a continuous graph, we just keep on going right through that function value. When the graph is discontinuous, your limit and your function value may not be the same. So let's look at what happens as x approaches 2. Well, the limit is x approaches 2, so we're just going to walk on this function from the left, and then we're going to walk on this function from the right. And are we going to hit into each other if we just keep on walking? Yeah, absolutely. Absolutely. So the limit from the left is equal to the limit from the right. So what are they approaching? They're actually approaching 1. And then what is the function value at 2? Well, there actually isn't a function value. There's nothing defined there. There's no solid dots, so it does not exist. The function just doesn't happen at x equals 2. What about when x equals 3? What's our limit as when x equals 3? Okay, so if you notice x equals 3 is an asymptote. So what happens as I approach this limit? As I approach 3, I am going to negative infinity. Again, remember the limit is a y value. So what happens to the y value as I approach 3? I'm going to negative infinity. I'm getting just hugely big numbers in the negative direction, right? And then what happens from the right? Same thing. Same thing from the left and the right, which means the limit exists-ish. Okay, here's the thing about infinite limits. When something is going to infinity, infinity is not a number. Okay, so I just told you a second ago that the limit has to be written like this and the answer has to be a number. So is infinity a number? No. So in true, like, pure mathematics, if the limit as x approaches some number, like as x approaches 3 is negative infinity, then the limit doesn't really exist, right? Because it's not limited. There is no like spot where it just kind of stops. But to help us understand what the function is doing, we often write negative infinity because it tells us what's going on. It tells us that the function is getting really, really like hugely negative. So either one works here. You can write does not exist because officially the limit actually does not exist, or you could write negative infinity. And I would write negative infinity if I were you because it just gives you more information about the function. What is the function value at 3? Well, it does not exist at 3 because it has an asymptote at 3, so nothing, there is no function value at 3. All right, what about the limit as x approaches 5? Okay, so remember I talked about that it has to be like a clear path, right? So it has to be like 2 people are walking on this, so I'm walking here. Let me go ahead and draw that in. Say I'm walking on the function right here, and you're walking on the function here. It wants to draw. It doesn't want to draw there. There we go. You're walking on the function here. Are we going to hit at 3? Are we gonna cross paths? No, we're actually not gonna cross paths. There's a jump discontinuity here. So since the limit from one side doesn't equal the limit from the other side, this limit actually does not exist. So for a limit to exist, the limit from the left has to equal the limit from the right. They have to cross paths. And then what is the function value at 5? Well, which one of these is filled in? It's right here. So the function value, remember the function value is the y value. So the function value is 2. When x equals 5, y equals 2. So the limit doesn't exist, but the function does exist at 5. I know, blows your mind, right? Okay, so let's talk about one-sided limits with this. And you're going to see this notation here as x approaches 5 from the negative side, which I think, you can think it comes from the left if you want to think about that. But I just think it comes from the negative. Like, it's actually really easy to think about, right? From the negative side, as x approaches 5 from the negative side, what's going on? It's getting really, really, really close to 1, right? So one-sided limits, if the limit doesn't exist from both sides, then the limit doesn't exist, right? Like on number 5, the limit just does not exist because it doesn't approach the same number from both sides. However, we can then evaluate one-sided limits and we can look and see, okay, from the left, what is it doing? From the right, what is it doing? And we can write those down. So the first one was from the left side, what's going on? Well, it's getting really, really close to, did I write 1? That should be -1. You probably caught that a long time ago. And I was just sitting here yabbering along. All right. What happens from the right side? If you're coming from the right side, what number are you approaching? You are approaching 2. So this little plus sign here says when we're coming from the positive side, what's going on? And this one says when we're coming from the negative side, what's going on? What number are we getting really, really close to? So since those two one-sided limits do not exist or do not equal each other, the limit as a whole does not exist, but we can evaluate one-sided limits all on their own.